In the next example, we use a law from physics. Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So f of x is equal to kx, where k is a positive constant called the spring constant. Hooke's law holds provided that x is not too large. So let's take a look at figure 1. So in this scenario, this is where the natural position of a spring, and this is a frictionless surface. Now if you look at B, now that the spring is stretched of the spring, you can see what's happening, that now it's going from 0, then you have this value of x, and now this function, f of x is equal to kx. Now for example number 2, work needed to stretch a spring. Now a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching a spring from 15 centimeters to 18 centimeters? Now according to Hooke's law, the force required to hold a spring stretched x meters beyond its natural length is f of x, which is equal to kx. When the spring is stretched from 10 centimeters to 15 centimeters, the amount that's been stretched, it's gone from 10 to 15, is 5 centimeters, which is equal to 0.05 meters since we're making that conversion. This means that f of that value of 0.05 meters has an output of 40. So therefore, 0.05 k is equal to 40, and now we need to solve for the constant. Dividing both sides by 0.05, k is now going to equal 800. Thus, if f of x now is equal to 800x, and the work done in stretching the spring from 15 centimeters to 18 centimeters becomes the following integral. Now w is going to go from the integral from a lower limit of 0.05 to 0.08, 800x dx. Which is now equal to 800 times x squared over 2, going from 0.05 to 0.08. Evaluate the limit, which gives us 1.56 joules.